Hi students, Miss Vernon here, and I'm here today to talk with you about the second day of 1.2, which is more properties that we'll need to know. So again, remember 1.2 has a lot of vocabulary. And it's really important that you understand this vocabulary, but also that you can continue to use this vocabulary as we move forward. So today's vocabulary that we'll be focusing on is extrema, which is really a fancy way to say what is the maximum and what is the minimum of a function. Increasing and decreasing intervals, that's going to be written in interval notation. And then we're going to talk about symmetry. Now, symmetry is something you've talked about in geometry. It has a visual component, but it also has an algebraic component. And for pre-calc, we're going to be looking that you can show me algebraically that a function is even or odd. And I'll be teaching you how to do that today. All right, let's go ahead and get started. So to begin, let's focus on maximums and minimums. So this vocabulary, if you see it on a slide or on homework, they might call it extrema. And so extrema is basically a way of saying, hey, what is the maximum? What is the minimum? Now, they refer to, or the book defines it as the maximum is the highest point on the graph and a minimum is the lowest point. Now, notice that these graphs are continuing on in this sample. So we don't consider an undefined stopping point a maximum. So we do look for where did it change from going up to going down. And we consider this to be the maximum. And where did it stop going down and start going up? This is considered to be the minimum. Now, a graph can have more than one maximum and it can have more than one minimum. And then I just want to put one more comment out here. Be careful because sometimes it just asks for the y value. So be careful here. When you are answering the questions, they may just ask for the y value or the y coordinate of the maximum and minimum. And sometimes they want the whole point. So reading the directions is going to be very important. All right, moving on to the next vocab. See, the early vocab in this one is very quick. All right, change in functions. So when we're talking about a change in function, a function can be increasing. And I caution you on this. The book defines it as if the y value increases between 2 points on the x interval, which is basically a fancy way of saying as you trace the graph from left to right, are you tracing and it's going up or is your finger going down? That's kind of the basic way of thinking of it. If it's decreasing, we say that it is the y value is going to decrease between 2 points on an x interval. Okay, and I've got a lot of examples to show you this. And then the third type of interval of change we can have is what we call constant. And if a graph is constant, the y value is going to stay the same. So there won't be any change in the y values. It'll stay the same between 2 points on an x interval. So those are your three types of change you could have in a graph. Now what I'm going to do is I'm going to show you an example of each of these. So for the first one, we say this graph is increasing. Sometimes they'll say it's increasing on the domain. Other times they'll say it's increasing from negative infinity to infinity. And the reason why is as I trace this graph, and I always go from left to right, my cursor or my finger would always be going up, even if it slows at certain points. The next graph, or the second graph in this line, is going to be a decreasing graph. Again, as I trace it, my cursor is always going down. So this is considered to be a decreasing graph. And again, we might say it's decreasing on its domain, or you might say it's decreasing from negative infinity to infinity. And then the third graph is constant. Notice that the y values are not changing as I trace this function. It's just a horizontal line. So again, constant on domain, or you might say it is constant from negative infinity to infinity. And then these are very, probably more of your anomalies, not common to see that, but a graph like this might be more common where you have some points of change. And so I've written these out ahead of time. So this graph would be decreasing from negative infinity. So notice that it continues on forever here. So it's going to be decreasing, and then it stops decreasing at -2. Now, we always are going to use that hard bracket because we're talking about it on an interval of time. And so that x coordinate is always included. And then we see that it is going to be constant between -2 and +2. So notice again, we've used hard brackets on here because we're indicating that between those two values, those two x values, or that x interval, the y values are not changing, they stay the same. And then we continue to increase after that point. So therefore, from 2 to infinity, we are increasing. Again, notice that we're always using those hard brackets. And again, that is because we're saying between these x values, or on this x interval, this is what is happening. All right, so I have another one here. This is an example for you to kind of pause the video, take a second, look at it, see if you can find the extrema and the intervals of increasing and decreasing, or constant if there are any. All right, I'm going to go ahead and start by identifying the extrema. Now, sometimes they will use the word local maximum. Basically, that's just saying, based on this graph, what we can see, the local maximum is going to occur at -1, 4 and 5, 5. Now, if I said, where is the maximum happening at? You would say y equals 4 and y equals 5, because those are the two y coordinates of where the highest point is occurring. Just like we have a local maximum, sometimes the book will refer to it as a local minimum. And we only have one local minimum here. That's going to be at 2, 2. And again, sometimes they reword it and they say, what is the y coordinate at that minimum? And so we'd say y equals 2. All right. Next, it asked us to determine the increasing and decreasing intervals. So I'm going to just go ahead and kind of sketch my graph, and I'm going to go, okay, we're going up. I always start from the left side. At this point, at this x value, which is -1, because we have that point, I am no longer going up. Okay, so when I switch to going down, I'm going to change my color of my pen. Now I'm tracing the function. My squiggle line is going down, and it stops going down when x reaches 2. All right, then we start to go up again. So I'm going to move up, 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 and we stop going up at the 5 value. And then our graph changes direction, and we are decreasing again, or going down. And we continue to go down until we reach that infinity mark. So at this point, what we're going to do is we're going to just write our increasing and decreasing intervals based on what we just traced of our function. So I'm going to say we are increasing from -infinity to -1. And then we're also going to be increasing from the value of 2 to 5. Again, these are always the x coordinates. Notice this was the x, this was the x, and then here we have that x coordinate again. And then we're going to write our decreasing intervals. That's where we were going down. And we were decreasing from -1 to 2, and from 5 to infinity. Now, I apologize. These should be hard brackets up here. Sorry. There's a hard bracket there. And then there's hard brackets on each of these as well. And I apologize. Sometimes we get so used to those parentheses that we forget those hard brackets, but hard brackets because it's on that x interval. Awesome. Let's move on and take a look at what symmetry is. So we have two types of symmetry that we will be looking at. We have what's called even symmetry. And even symmetry, or an example of an even function, would be y equals x squared. And I have that one graphed here right on the right side. And when we're talking about an even function, we have symmetry on the y-axis. And so the y-axis is the vertical axis. So it's this one right here. And basically what it says is if I were to fold this out over the y-axis, it would be the same on both sides. I like to call this butterfly symmetry. So symmetry about the y-axis means if you fold on the y-axis, you would be the same on both sides. And again, I kind of sometimes refer to this as butterfly. We have the same graph on both sides, and that center point is always the y-axis. To show algebraically, so this is the visual piece, and this is the algebraic piece. To show algebraically, we have to show that the original function is equal to the original function when you replace all the x's with negative x. All right, the second type of symmetry we might have is what's called an odd function. An odd function will have what we call rotational symmetry, which means that if I were to take this graph and rotate it 180 degrees, so flip it upside down, the graph would look the same as it did originally. And again, you should be able to rotate it again. Now, one important component is that you do need to rotate the graph a full 180 degrees. And so sometimes I'll see students in class, even though it sounds super silly, they will actually flip their calculators upside down to check when they're looking for that visual check. But then to algebraically check, you would have to show me the algebra that I've given here, which is you show that negative f of x is equal to f of negative x. Now, again, this is the algebraic piece. You have to be able to show those algebraic pieces in order to get credit. And so I'm really going to be holding you true to that. I'm going to show you a whole bunch of examples, and I'm going to explain a little bit more about how that looks. So how do you algebraically show this? The first thing we always do, or the first thing I always encourage students to do, is I always tell them check to see if it's even first, because in proving if it's even, you will already do one of the steps to show that it's odd. So to show that it's even, you have to make sure that the original function, f of x, is going to be the same as when you replace all the x's with negative x and simplify. So what we do is we first find out what is f of negative x. To do this, we replace all of the x's in the equation or the function with negative x, and then we apply our simplification rules. So if it's a negative x squared, that would become x squared. If it's the absolute value of negative x, it becomes positive x. So we apply our basic rules of algebra. Then the last step is we check, is the original given function the same as when we went and plugged in negative x for all the x's and simplified? If this is not true, then we move on to step 2. In step 2, we're going to check to see if it's odd. Now, to show that a function is odd, we have to show that when we replace all the x's with negative x, that becomes the same as when we do negative f of x. Now, remember, we've already shown this in step 1. So we've already done one part of this. So next, we're going to do the second part. And to show the second part, you're basically just going to distribute a negative 1 through the function. Okay. Now, if this is not true, then we simply state that it's not even, it's not odd, therefore it is neither even or odd. Not all functions are going to have symmetry. Let's go ahead and take a look at a couple of these together. So in the first one, the function that we're given, so the original function, is given here, f of x equals x squared minus 3. Okay, so my first step that I always follow is I'm going to check to see, is it even? And to check if it's even, I'm going to have to show that f of x is equal to f of negative x. Well, we already know what f of x is. So I need to show what is f of negative x. So f of negative x will look like this. I'm going to replace that x with a negative x, and then I keep everything else the same. Now, when I go to simplify this, I know that negative x times negative x is positive x squared. And so this is what f of negative x becomes. Now, visually, I can see this is going to be an even function, but I've just algebraically shown that this is the same as this, the original. And when those are the same, I can say f of x was equal to f of negative x, therefore even. Now, as soon as you know it's even, you're done. You don't have to move on and check to see if it's odd, because if it's even, it's not going to be odd. And if it's odd, it's not going to be even. So you only have to go until you figure out one of them works. All right, I have a second example here, and then we're going to wrap up this video. So in our second example, we are given that our starting function is a g of x, and g of x is equal to this. So again, I always start with the first step is checking if it's even. Now, I can look at this graph and go, well, it does not have symmetry on the y-axis, but we're still going to do the algebraic check. You must show the algebra even if it can visually be checked. So to show if something is even, you're going to have to plug in negative x for all the x's. So I'm going to go ahead and, let me change out that f for a g here, since this initial function was a g. All right, so we're going to find g of negative x, which in this case would be negative x squared minus 2 times negative x minus 2. Well, negative x squared is a positive x squared. A negative 2 times a negative x is a positive 2x. And then the last is just a minus 2. So as I look at this, I go, this is not the same as what we started with. Therefore, is it even? Nope. So it is not even. So next, I'm going to go ahead and do my check to see, is it odd? Now, recall, we've already checked the first part of it. To check if something is odd, we have to check that g of negative x is equal to negative g of x. So remember, g of negative x is right here. It's that one we learned about just before this. And so now to show negative g of x, all I have to do is basically distribute a negative 1 through this function. Now, some of you are already ahead of the game and you're like, there's no way that can become the same as what we just got in the previous problem because we have a negative x squared as our leading term. Therefore, I now ask myself, is this the same as what we had when we had g of negative x? Because again, that's our proof. That's how we algebraically show it. And it might be helpful to write them side by side if you are a visual person and you're like, Miss Vernon, I'm not seeing this. So what I'm going to do is I'm going to write that red function that we did above. That's g of negative x. And we're going to ask, is this the same as the blue function, which was negative g of x? And sometimes writing them side by side helps students see it better, but you should tell me, no, these are not the same. So therefore, it is not odd. And if it's not even and it's not odd, then it is going to be neither. All right. So there's your lesson. I hope that you have a better understanding of how to algebraically show even and odd. And be sure to ask questions if you need any additional support. Bye.